Hi there, welcome back to our channel. And on your screen, you see a circuit of a differential amplifier using MOSFET or simply the FETs. So in our previous modules, we have analyzed the MOSFETs using the differential pair of BJTs, that is the bipolar junction transistors. And this time we are going to see the analysis for this circuit. So what you see, you have this voltage source VDD that is connected as shown, and to the VDD you have one end of the two identical resistors which are called as drain resistance because they are connected to the drain pins of the MOSFETs. So here that is the drain resistance RD. So that's your drain pins. These are your gate pins and these are your source pins. The direction of arrow in the MOSFET indicates the current is flowing from drain to source. It is coming inside the transistor from the drain terminal and it is leaving the transistor from the source terminal. Now that current, which is the source current of the transistor, let's say this is IS and this is also IS, that that is becoming ISS. So ISS is basically 2 times IS, or IS would be ISS divided by 2. This is called as tail current source because it's connected as a tail to these transistors. And the implementation of this current source by means of a simple resistor, or you design a special circuit which is called as current reference circuit, where you also use the current mirror technique. We have seen that in our previous module. Now I would say the IG is equal to 0, which is the current trying to enter the gate pin of the transistors. So here also IG is equal to 0. And that's your drain current. Let me write here drain current ID as shown by the direction of the arrow. Now, there are two inputs. That is the input 1, let us call it input 1, that is applied to the gate of transistor M1, and input 2 that is applied to the gate of transistor M2. And for this particular circuit, we have tied both the inputs V1 and V2 together, making it to be a common mode voltage indicated by VCM. So VCM is your common mode voltage. Common mode voltage. Now the advantage of, essentially it is a difference amplifier. So advantage of applying a common mode voltage to a differential amplifier is that this is your VCM here, and this is your differential gain. So output is gain times VID, and since your VID is the difference between V1 and V2, and now VCM is basically common to both inputs. So therefore, there is the difference between the two inputs is 0, and therefore the output is also 0 ideally. So that's the advantage of difference amplifier. It rejects the common mode signal and it doesn't provide any output for the common mode signal. However, for the case of differential amplification, where each individual inputs are having a different magnitude, you have output that is gain multiplied by the difference between the two input. And that is how the differential amplifier works here. So the current that is being taken from the circuit consisting of resistor and the MOSFET, That's the current, and essentially that current flows through this transistor M1 and M2, which is a drain current, and drain current is equal to the source current. So let me write here, ID1 is equal to ID2, that is the drain current, and we can write also here, that is IS1 is equal to IS2, and that is equal to ISS by 2. We are assuming here the gate currents IG is equal to 0, obviously. And now we see that the transistor M1 and M2. So let me just clear this drawing a bit so you can understand it in a much better way. So what I'm going to do here, after explaining you the concept of the currents and the voltages here, let me draw the voltage drops here. So when you apply the voltages, the voltage between gate and the source pins is called as VGS. Here also, the voltage between gate and the source is called as VGS. So here we say that VGS1 is equal to VGS2 is equal to your VGS. Okay, and now there is the difference. There is a differential voltage produced, that is VO1 and the VO2. So VO2 and the VO1 are basically your voltages at the drain pins of the transistor. These are your drain pins of the transistor. These are gate pins and these are source pins. Okay, now there is a one more concept called as VGS minus VTH. The difference between these two voltages is called as V overdrive, VOV. So that's the voltage you need to apply to these transistors. And the condition of operation of the differential amplifier is that both your biasing or the operating points or the bias points, which you will decide by choosing appropriate values of the resistors and the current in the circuit for a given differential or the common mode voltage, is such that your M1 and M2 both should be operating in the saturation region, and that is graphically illustrated by the IV characteristics of the transistor. So here is your ID versus VDS, and your transistor is ideally takes this shape, and the region right to this dotted line is called as saturation region of the MOSFET. The region left to this line is called as triode region or the linear region for the MOSFET. Okay, and this is your the cutoff point where your transistor enters into the saturation or the or the linear region. So this is you can call it as VDS minimum, and based on that you choose a point where you say that, okay, this is going to be my desired ID, and this is going to be my desired VDS. That's my Q point or the bias point or the operating point of the transistor. So the condition is that your VDS has to be greater than the V overdrive voltage. Okay. So it means when you have VDS greater than VGS minus VTH, then your M1 and M2 are in saturation region. Okay, and when it is less than or equal to actually. So that's how when you have M1 and M2 in the saturation region, they are going to provide a constant current. and they acts as a current sources, and then you have this trail current source, and the voltage VO1 and VO2 can be written as VO1 or VO2 can be written as VDD minus ISS by 2 multiplied by the RD. Remember, your ID is equal to ISS by 2, and that's your ID. And the current in the saturation, when your transistors are in saturation region, you have the value of the drain current, ID sat, is equal to, you have this like uh, Kn dash mu into Cox, mu n into Cox, and then you have W over L, and then you say this is VGS minus VTH, okay, and in bracket 1 plus lambda VDS. So lambda is the channel length modulation parameter, which says or indicates the variation of the drain current with the increment of your VDS, that is applied electric field. So when lambda is equal to 0, you have the green curve, a constant, the slope is 0. And when lambda is not equal to 0, you have a red curve where you have a small increment. So basically you have the delta I was divided by delta V. So that is a transconductance of the output transconductance of the MOSFET. So that's your current equations for the transistor. This is applicable to both the MOSFETs, that is M1 and M2. So the current flowing through the MOSFET is given by this equation. Okay. So hope you understood the basic about MOSFET differential amplifier, and for low power application or for higher input impedance, which MOSFET offers, your differential amplifier using MOSFET is preferred over the differential amplifier using BJT. So if you have some comments linked to this explanation, put it in the comment sections, and hit the like button, subscribe to the channel, and stay tuned for more engaging content like this. Till then, wish you happy learning.